All right. The stream is on. So for everyone watching, me and Richard, say hi, Richard.
Hello, everybody.
So Richard's here with me, and we've been discussing what to do, and we've come to the conclusion that we think, according to Dr. Hastings' information, that the collapsing magnetic field produces a pulse in the magnet, which pulls it, so speeds it up. And then during this cycle, the induced magnetic field through the arc can actually go in reverse. And there's many indications from my memory that this makes perfect sense, that the current only happens at a certain time, and it happens through the arc, which is why you have a lot of nasty RF in some of those other persons, J.L. Noddings and Stefan's work, and Newman. Hastings also describes it that way. So the idea here is to get the thing spinning outside of the induction window, and then pulse it at that rate inside that induction window to just keep the arc flowing negative current and not positive current, and that allows the current to not be impeded in the wrong direction from the battery current, but yet still be connected to the battery through an arc. Very confusing, but that's actually what appears to be what's happening. And there's a document, unfortunately, or fortunately, I don't know yet, but there's a document here. Cannot be seen on the live stream. Well, let me actually turn that on. There we go. So you're not going to be able to read it very well, but there's a document here that we are going over, and it is actually written by Ralph. And Ralph, if I'm not mistaken, worked at the power company. I think.
By Ralph. And Ralph, if I'm not.
I can hear your audio, Richard.
The power company.
I can hear my audio and your audio. Your video's playing somewhere.
Ralph. And Ralph, if I'm not hearing audio with the power company.
Yeah.
I can hear my audio and your audio. Your video's playing.
I'll let you find it. I'll mute you until you find it. Anyway, so the idea here is to use this information. This is a commutator overview information, and we're going to use this information to just slightly get an idea of what we could possibly set up to match similarly what we want to achieve. Did you find it, Richard?
Slightly get an idea.
No, you did not. Richard, find the window that's open. I can hear your feedback. I can't play your audio unless you turn off the window. Do. Did you find it?
Play your audio unless you turn off.
Nope, not yet. Oh, now you found it. Can you hear me, Richard? Oh, he muted himself now. I unmuted you. You have to unmute yourself. You'll figure it out eventually. What? Oh, now I can't even unmute you. What'd you do to your audio? You broke it. Anyway, I'll let him figure that out. So this information is not by someone who has high-level experience, but was around Mr. Newman for a lot. Yeah, but I don't know how to fix it. I muted everything, but now I can't hear Russ. Unmute everything. Close tab from stream. Oh, now I can hear you, Richard. Talk.
I don't know if you can hear me, but I can't hear you.
I can hear you just fine. So unmute your playback. Do 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 do.
Okay, I unmuted my speaker.
Oh, can you hear me now? There you go. You can hear me, right?
I think it's
Muted my speaker.
Your playback is coming through the stream, not through Zoom.
You can hear me, right?
So turn off the stream so that you can hear me through Zoom. He broke it. I'll keep talking. We'll reconnect if it doesn't work. Russ says this is actually rocket science. Okay, so now, okay, can you hear me now, Richard? Where is this doc? Oh, you said, Steve, you don't have, which doc? The one I'm reading right now? Everything's posted at the forums, all this stuff. Go read the last 3 pages. Richard can't hear me. Well, we got to fix this audio problem, or we're not going to be very good teams here. Fix your audio. I'll be back in a couple of minutes. What? I can hear his audio. Okay. Well, while he takes a break, I'll mute him. Maybe he's trying to get his headset. Okay, so in the meantime, this little document is written by, like I said, the guy Ralph Hartwell. I think Ralph is the one who, from my memory, was the one who worked at the power company. So he wrote this document, and it specifies in here some interesting points, and we, like I said, discussed the information already earlier. If you missed it, you can watch the beginning of this stream. But basically, the information leads us to pulsing or arcing the commutator at the induction stage, while the rest of the stage is actually doing the power stroke. So the power stroke will have to be before and after the induction stage, which is actually right dead smack in the middle. So we're just going to cut some breaks in the commutator so that we can test out this simple thought. And let me pull up some screenshots so I can explain to you why this makes sense to do. Let's see. So, you need to open up this folder. And here. And scope. Oh, this one. Mine. Scope and notes. Let's see. I'm gonna have to open a new window to get this to work, probably. Okay. So the question that we had earlier was pretty simple. Yeah, he's putting on his headset. Okay. So I need to I guess I could try capturing. Let me just add a. Let me just do the screen. I'm just going to do window capture. And I'm just going to do that one. See how that looks on the. Oh, that's a mess. There we go. Alright, for now, this will work. So you can see my mouse. Oh, Richard left the meeting. He'll come back. Okay, so why are we doing this? So let me explain. Okay, so let me explain to you a few things here. Without too much chaos, so we turn on the power right here, and then we get current. There he is. Oh, now you have no audio input. Richard, if you can hear me, you have no. Oh, there you are. Hello, can you hear me now?
Yes, I can hear you.
Can you hear me directly? Hello, 1 2.
Yes.
Oh, okay, so find the tab with the stream and turn it off, and then you can open up the chat tab only. The chat tab only is the same place as the live, but just with chat afterwards. So it's like that. I put it in the chat post, if you can find it. Oh, you fell off again. There. Anyway, we need to fix this issue so I can concentrate. Maybe. Ah, well, this will be an interesting stream. We'll fix it. Ah, you don't need to see me. Do 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 do. I need to find my notes anyway. Oh, you all just have to scroll through this live stream to find the bits and pieces that we're working on, but I don't have. He broke it. Oops. That was mine. Oh, you're back. He's back. Alright. Now, you probably have to set up your audio correctly on Zoom. If you can hear me, Richard, open up the chat. I don't know where it's at, to be honest. Oh, there you are. Can you hear me? Okay. Hello, 1 2. Do 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 do. Through the live stream. You can't hear me at all through the something that, I mean, I can't hear you at all. Let me just reinitialize my audio. Speakers. Hello, 1 2. Hello, 1 2. Okay, everything is working on my side. What do you mean it goes nuts? Because it's not going to work if you're not here with me. This is broken. We got to fix this. Yeah, please show me. Go into the Zoom settings and make sure you got the right things on. Okay.
Okay, I should be on now.
I can hear you just fine. Can you hear me? Nope. You can only hear me through the stream.
Yeah, I can hear you.
It's delayed though, so it's through the stream. Which is a bit weird because I just tested my audio and it works just fine. I don't understand why you can't hear me through Zoom. Maybe you need to close the live stream.
Okay. Okay, I closed the live stream. Can you hear me now?
I can hear you just fine.
Okay. I turned off live stream.
Yeah, that's the whole problem. You can hear me
Okay.
now. You can hear me now, right?
Yeah, I can hear you fine.
Yeah, I've been trying to get you to do that for 10 minutes.
Sorry, I didn't understand what you wanted me to do. I'm sorry.
You can open up the chat. I put the chat in the Zoom chat. You can open up chat only. Don't open up the whole stream box.
Okay.
That way you can still see the other chat if you want.
All right.
All right, you're all set, right? We're good?
Yep.
Okay, all right. Good. Glad we got that figured out.
I'm an old man. You got to give me
Slacker.
some slack.
A slacker, see? I got to give you slack so you can be a slacker.
I'm a slacker. Yeah, I'm a slacker.
Yeah, we're all slackers. Okay. You can see my screen, right?
Yep.
So I'm trying to explain to the stream why we're doing what we're doing.
Okay.
And so I'm trying to explain the scope shot, and then I'm going to give you a RPM value according to what shot we want to pick here.
Okay.
So according to these scope shots for the live stream, if you, one of the questions posed is if you're inducing voltage into the coil while trying to spin the magnet, does it slow down the magnet? I actually think it does, and I think it does due to some of the scope shots here where I show here is a big ring and here is no ring, and the difference between these two is a short, and you can adjust the ring by how much current is flowing in the coil. So I think that, yeah, if you truly have back current, then that doesn't work. So what we want to do is, if we go to let's go to this screenshot here. So we turn the coil on, and then this is current going from the battery to the coil, and then the induction starts, which is this curve going up, this curve going down. This is voltage on the batteries. So the voltage on the batteries actually gets above the battery voltage, and the current actually goes below here. The bad thing here is we're fighting the induced current. I mean, we're fighting the EMF and the back EMF. We're fighting it via the battery being connected. So how do we do that? So we can generate a spark and let the spark send the back current the wrong way. So what we want to do is, during this short cycle of induction, we want it to be basically an arc, and the only way really to do that is to turn it on and off rapidly, or have a bad brush contact there or something. You know, I could even Richard, I could even sand that part of the contact and make it super rough and give us a really nasty contact. That's an option.
Yeah.
That's actually something that JL Notting did, I think. So, with that said, we'll go to a different screenshot here, and I'll show you the negative current for people who don't know what the heck we're talking about. So here, let's start right here. So here we have shorted the coil, and it's got some energy left in it, and so when that energy left in it gets here, this is energy left and induction all at the same time, and we get this very large negative current spike, and then it goes way up, and then this is a gap between two pieces of copper on the commutator. Then we keep charging, and then we do the reverse. So the blue line is current from the battery, and the green one is current in the coil. So you can see right here the current starts going down, and then we turn it on, and then we short it, and it goes down. This is the decay with no ringing. There's no ringing going on here. So we want this fast, the interaction right here. We want this interaction right here to happen with no imposed EMF, which means no voltage from the battery. We want only the induction currents to be going the other way into the battery. But how do you connect the battery to the device when it's going in the wrong direction and all that nonsense? And you do it through the arc. Okay, now that I got all that out of my head, I will turn that off. And try to turn this paper back on. This document, let's see. That one. Oh, it's not on though. There we go. Okay. I'm gonna have to go fix everything because I screwed it all up. This is fine for now. I'll just put this here. So, alright. So, this is again reference material that I'm taking with a grain of salt, but hey, it's fine. So the normal polarity reversal position is about 10 to 15 degrees past top dead center, or the position where the magnet is parallel to the axis of the coil, which means the magnet,
down.
yeah, okay, so parallel and parallel. Polarity reversal is about 10 to 15 degrees past that, which is actually pretty close to what we measured on that image.
On the picture, yeah.
Note that the position of the reversal is adjustable by changing the angle between the magnet and the commutator. Polarity reversal position. The most common effect operation, the most efficient operation is not the position where the motor runs fastest, but rather slightly before that position or advanced in timing. If this were an automobile engine, this requires a bit of playing with to get it right, blah, blah, blah. Okay, so now he gives us a parameter, and so we're going to try to work through these and see if we can come up with something interesting to just try while we're doing this and thinking about it. This may not be exactly what I just talked about at the beginning of this video, but we're going to try this first just because it's here and we can do that. So determine the time required for the current to rise to the maximum value through the coil in the motor. This may be determined by connecting the motor coil to a battery with a small resistor in the series. Okay, so we can measure the time constant of current. So I don't need to do that. So what do we want to do? Do we want to go up to 600 volts? Because we know we can run it. We can run it at 300 or 600 with no real problem. But I think 600 is probably better, just because we can get a higher RPM out of it. Richard, so we want to.
Yeah, that's 600 is fine.
Okay. All right. So decide the speed in the RPM at which you are going to have the motor operate. Remember, this is unwise to have the machine too fast. Blah blah blah, because it'll explode and you will die. Calculate the time required for the motor armature to rotate at the RPM you have chosen. Calculate the time required for the motor armature to rotate one time at the RPM that you've chosen.
So in other words, if you're going at 120 RPM, it takes a half a second for one revolution.
Okay. So now we need to calculate the time for the current to rise about 20% of the maximum value determined by step 1. So we need to we can either do one of two things. We could get new data, or I could pull up our old data, which I think is what I'm going to do. So let me go find our old data. Let's see.
I don't know if we never did really determine accurately what was 90% though.
We did 70 something. Well, we can do it here. We'll do it now. So let me affix the live stream and you. Let's see, you can see my box now, right?
Yep.
Okay, so let me turn the scope back on here and fire that up and get that going on the stream so we can all see it. Takes a minute to fire that thing up. All right, so 600 volts. Well, it's not actually 6, but we'll figure that out in a second. So let's see, I need to actually disconnect some stuff. So I'll just take off the whole entire brush holder assembly. And therefore, everything is disconnected. How about that? I need to also lock the rotor, I guess, so it doesn't interfere with anything.
Or you could just temporarily slide it back to the other edge.
I got too many wires connected, I think. Actually,
okay.
Actually, no, I can remove the entire thing the way I got this set up now. How fancy. Look at that. What a dream. Okay. I'll put that down there. So now we got access straight to this. No magnetic interference. I'm sure that guy will turn down there. Remember, we tested that.
Mm-hmm.
That thing was turning all the way down there, really.
I know it was.
Okay, so I'm just going to take a jumper and I'm going to go from one of the power leads to one of the coil connections, and I'm going to go from the other power lead to the other coil connection, and then we can measure current in two locations. So we got current covered.
Don't forget to zero your probes.
Yeah. Actually, I should have turned this stuff on earlier so it's all warmed up, because it could change a little. It gets pretty hot. Everything gets pretty warm. All right, so oh, hold on, I gotta fix this. There we go. All right. You can see that okay, Richard? It's probably kind of small for you.
No, that's good.
Okay. All right. Very good. So we're just doing a charge constant. So he says 90%.
Yeah, well, the scope will it calculate 90% for you?
Remember, I don't know if I ever figured that out. I don't know if I've ever figured that out. We just need to. No, I don't know if I don't think I ever figured that out.
Well, we can guesstimate it.
Yeah. So I know this is really small for you for now, but at least you can see that.
I can see it.
Okay, well, let's. I need my flash drive back. I need to set up a folder and I need to save everything so we have a reference point. Gee whiz, it's 5 o'clock. We're not going to get this done. Oh well.
Man, it's 8 o'clock.
That's alright, we won't get this done probably, but we'll get a few points down. Probably have to continue this tomorrow. Do.
2.7, right?
Yeah. Two 7 18.
Man. I was born in 1949. It's hard to believe it's 2018 now.
It's a long time. Alright. That's all fine and dandy. So our battery voltage is 578.
578, okay.
0.3. Now the scope, however, is a little different. It's at 577.4.
I think that's just the difference in the calibration of the two instruments. That's, you don't have to worry about that.
Well, I think it's actually the noise on my probe, because it's not supposed to be reading this tight tolerances.
Yeah.
Which actually is pretty good for being that, because on the 6,000 volt peak to peak scale, it's huge.
Yeah.
Okay, so if I connect that wire, we should charge the guy up. So I'm going to charge the guy up. Oh, I don't have the... Realistically, I need to go back to this. There we go. Which... Oh, that one. Okay. Alright, now we can see everything. Oh my gosh. Stomach hurts. Can you tell? I don't know if you could hear that. Hopefully you could not.
Are you okay, buddy?
I might have to leave the room. Okay. Alright, here we go. I'm just going to charge this guy up. Ow. shocked me.
Are we going to see if the charge time and the discharge time are equal? I mean, they should be, but
No, because I'm not going to short it out.
oh,
I'm just going to connect the coil and let it charge, and then once it's fully charged, I'll just take it back off, and then we'll take that measurement.
okay.
I actually don't want to do this with this lead. I want to use some other crappy lead so I can burn those off. Alright.
Well, it's only going to draw a couple milliamps. I mean, 6
Yeah, but-
milliamps maybe.
But it'll eat the coating off my probes. Anyway. Okay, here we go.
All right.
Oh, what is that mess?
Nice.
That is... Alright, I'm on 1 million points. Let's go see what kind of mess we got in there. Look at that mess.
I think we need to redo that measurement.
Wow. What a mess.
Oh boy. You almost need a mercury wetted relay to do it right.
Oh. Why didn't you just tell me so? I have some.
If it's like a 6-volt relay or something, you could just use one of the other batteries to trigger the relay.
I actually have a mercury switch. Actually, which would be a good idea. Let me just go get it. I'm pretty sure I know where it's at. Not like we have nothing else to do. I believe, as long as my... I think it's in there. Oh my gosh. I gotta get my stuff put back eventually. Put away. There is no a way to put it at the moment though, so that's the problem. However, this box has the proper things in it. There it is. Sweet. Someone put it back. Good job, someone. Probably me.
Good job, Russ.
Now if I just don't drop it, 'cause it will shatter.
And doing that.
This is a good idea. I need to put this on a little turning rocker so I don't have to touch it. So I guess I'll use the most farthest away, which is that one. You're so smart. All you had to do is tell me to get my mercury switch, and I'd have done it a long time ago. Because actually I can do different things with this. Alright, let's try it and see if it throws a giant arc and blows up.
Yeah, hopefully not.
I need to go.
Look at that. That's pretty nice.
Yeah. Way better than what we was trying to do a while back. Jeez, like what were we doing?
Man, technology, woo!
Look at that instant voltage.
Oh man, is that sweet or what?
Let me do this again with a closer. I don't need to be so. Let me just try it like this. Oh yeah, it arced. I heard it.
Oh.
Okay, cool. So that's that. That was easy.
Man, that's awesome, Russ.
Yeah, should have told me to do that a long time ago. Why'd you wait so long for?
I just remembered about mercury switches just now. I don't know.
Well, I'm glad you did.
I'm an old man. Cut me some slack.
Oh, currents does not real zeroed there. I want to see what happened right here.
You
So
gonna put your cursor marks on there so we can see them, or?
well, I need to reset the. I'm trying to get a few things set up here. So the currents, they're all fine. Let's see if I can go in. I should be able to go in there, so we'll get a little bit better voltage reading. Current, I can't change the currents. Looks like I've got this backwards though, so I'll switch it around. So the green and the blue are in the same direction. So let me zero everything again. I think I can. Okay, I'm gonna do this again. I'll try to do it faster this time. Cool.
How much did that battery voltage drop?
Let's see. Battery voltage went
not
from.
much.
Whoops. Went from
About 30 volts, a little less than 30 volts.
22.23 basically.
Okay, so
I'm gonna save this. Okay.
all right. Man, that sure is a nice clean turn on.
Yeah, I mean, there's a little peak there, but it ain't much.
Yeah.
Kind of want to look at.
We want to try to figure out 90% of the rise time.
Yeah, there ain't much of a little peak there. That's 4 milliseconds, so you know, there's a tiny bit of noise.
Yeah.
So let's say
it's better than clipping two clip leads together.
okay. Yeah. All right, I'll just use the voltage marker. Actually, no, I want to put it on the current. So the blue one. Okay.
%.
So let's just see, the total current is like,
Yeah.
you know, 33 milliamps. I just want to see. Okay.
32 milliamps per second. That's the,
Oh yeah, right.
That's the.
Oh yeah, the delta's only. Oh, I was reading the wrong one earlier. The delta's only 12.
Right.
What was the? That one's 22.
90%
okay.
of 12. Let me see here.
12.2.
So Move your cursor till it gets to 10.8 volts, and that'll be your place for the second cursor.
10.8 volts or 10.8?
10.8 milliamps. 10.8 milliamps.
Yeah, okay. I'm not so sure we can do it that way.
Oh.
Because the curve depends on.
Well, that's 90% of the 12 milliamps.
Yeah, but then you got to do the curve. So like the last part of that takes a lot longer to level off. You know what I'm saying?
Right, but what does the instruction say? Determine the time required for the current to rise to a maximum value through the coil.
Yeah, which is 12 point.
Measure the time for the current to rise to about 90%. Now, it doesn't say the area under the curve. It says measure the time that takes current to rise to about 90% of the maximum value.
All right.
So that's
all right. Well, that time value is about 127 milliseconds.
Okay, that's good. Let me write that down here. 127.
And that's about 10.2 milliamps. No squeezing sparks. You missed the first part of the stream, but it's okay. We're trying a few more variations of things and stuff. We're running down through one of those documents. Actually, not one of the documents I posted for you, a different one. Just to determine a few things. Alright, you got that all? So calculate the time required for the motor armature to rotate at the RPM you have chosen. So the RPM according to my other data, we're going to call the RPM we want to hit.
Okay, we'll call that the target RPM.
I mean, realistically, I don't know. We were running like 100 that whole time last time, and it was running kind of slow.
Yeah.
So maybe we should just do 100.
Okay. 100 RPM. So the time for one revolution is 100 divided by 60. 1.6 seconds. No. That's wrong. 0.6 seconds. So 0.6 seconds is number 2 there. Well, number 3. Number 3. 0.6 of a second, or 600 milliseconds.
Right. Okay. And then it says, calculate the time for the required armature motor RPM chosen. Calculate the time for the current to rise about 20% of the maximum value as determined in step 1.
Okay, so 20% of 12. So move your cursor over to 2.4 milliamps, your B cursor.
2 point what?
2.4.
Man, that's pretty close to what I got already. We were always running right around 2 to 3 milliamps. So that's 18 milliseconds, 18.2.
Okay, 18 milliseconds. All right. So that's you need to know how many degrees that is.
Let's see.
Um,
You got that document?
yeah,
Let me.
yeah, I have the document.
Oh, okay.
Hold on here. 600.
Divide the time per revolution by the time required for the coil current to rise 20% as determined in step 4. This should be at least 10 times and less than 20. At least 10 and less than 20.
Okay, let's see. Well,
So number 4.
18 milliseconds, 18.2 milliseconds goes into 600 milliseconds 32.96 times. Uh, 360.
Okay. 18.2. At least 10 and less than 20. Well, we're definitely above 20 if that's the case.
Right. The time per revolution divided by the time reached 20%. Okay, so that's 32.9. Basically, what that amounts to is it rises to 20% in a rotational period of 11.25 degrees. So the rotor has to only turn a small amount, 11 and a quarter degrees for the coil to rise that amount, 20%.
Okay. So if we look at, let me see. If I go back to actually I could put that right there. I will once I get the right folder open here. Let's see, let's just go to yesterday's. I'm going to put it right here so they can see it. So yesterday's, let me go into, we said 100 RPM, that's like 600. That's like pretty close to this shot. This shot's a little slower than that.
Okay.
This is 317 times 2. One on here was, yeah, okay, we'll just use that one. So if we look, if we start here and we say 18 milliseconds, this is on 100 milliseconds, so it's really, really, really short compared to this, like 11, you know.
It's basically one minor division on that scope screen.
Okay. So what I can do then, I can take my current commutator.
Well, actually, it's a half of a minor division.
I can take this commutator. It's on here. And I can just cut those notches in this one. This one's pretty haggard. I need to cut another one. Make it bigger probably. So look, I only care right now about the on time. Okay, so let's keep going here because he says...
Are you on step 6? Is that where you are?
Yeah, but we can't really do this exactly the same way. We're going to need to just sort of break it up with that time duration.
Okay.
So, because here it says, you know, divide the circumference, on number 7, divide the circumference of the circle into the segments as the end value. The length of one of these segments is the length that each, I think it's missing a word, conducting segment on the commutator must be allowed to the current derived value calculated. So really, right now, I only care about the on time. And what I mean by that is I can't really deal with too much of the segments. All I can say is I only want to turn this thing on 20% of its charge time. So I can mark,
Okay.
I can mark 11, I can mark, you know, 12 degrees or 11 degrees. I can mark that on here and I can cut this whole thing every 11 degrees, so it's on off, on off, on off, on off. Well,
I mean, 11 or 12 degrees. I mean, if 12 degrees is easier, you know, it's close enough.
well, my problem is that's pretty small, and I don't have enough tabs to solder. I could make that work though. I can just drill a hole right next to the copper and just barely solder it onto the side. Not a problem, I think.
I mean, 12 degrees would come out into an even number, you know, even number of divisions.
Yeah, no, we'll stick with 12. So we're gonna call it
And actually, if your cuts were 1 degree wide, it would be 11 degrees.
oh really?
Yeah, I mean, if you have 11 degree and then a 1 degree space, then 11 degree would be 12 degrees.
Oh yeah, but I can't do that. I need a big enough gap for the brushes to make. See, that's what I'm trying to say. We're not going to be able to use, like, hold on. So it says,
Okay.
polyfill settings, which is what happening placements calculate. Okay, obviously you cannot have the whole commutator preferably filled with the conducting segments, which is what happens when you place any segments on the commutator as you calculated
In step
here
4,
in
right.
step 4. To solve this problem, you can remove the conducting. You can
Remove
solve
one
this problem.
segment.
Remove one conducting segment and divide the
Right.
space, thus gain
But that's
between the
not going to give you
segments.
enough space. You're going to have to remove 2 or 3 or 4 of them.
No, I know. Must be even amount, sure.
Right.
When finished, you should have an insulating non-conducting gap between each conducting segment, which is between 1/8 and a half the length of one of the conducting segments.
Ooh, so if it's 1/2, that's 12, that's 6. So if you did it every 18 degrees and made a 6 degree gap, then that would be good.
Yeah, but my problem
I'm pretty sure we're going to need a pretty big gap.
I know, that's what I'm saying. Actually, I can file these brushes down to a ever so slightly more point if I really wanted to. Let's see, on one whole half cycle, this is fine. I think what I'll do is I'll just do this on 1/2 cycle. So,
Yeah.
so right now I've got 110 degrees to work with, okay? That's one of those
Okay.
full blank segments. If I did that, I need a
If you divided that into 6 pieces, you'd be good.
into 6.
Yeah.
Let me go get my angle making device. I'll be right back. I'm gonna leave your audio on, but I'll be right back.
Okay. I can. It's all right, buddy. It's all right. Yeah, no, you didn't stop the stream. Okay. Yeah, right. I'm sorry it took me so long to figure out to turn off my live stream. Yeah, when Ort came on, yeah. Yeah. I I'll remember it now after I got so embarrassed. Mhm.
Alright, I did have it on, just me. Okay, so what I'm going to do, I'm actually going to take these off here so I can mark this really good. So what do we come up with?
6 pieces.
How many degrees is that?
That's 110. Well, it's actually just a hair over 110 degrees, but
Let me give you the amount that I need between,
okay.
because that may change how many we're going to put on here right now.
All right. How much do you need in between?
Hold on, I got to get this off.
Okay.
Squeezing sparks. Are you listening right now? It's always easier just to talk to you than try to explain things. All right. So currently, with my actual commutator, the degree angle is approximately, we'll call it 5.
5. That's the space you need is 5.
Yeah.
Degree space. All right. So yeah, if you make it just a little bit bigger than that, make it 6.
Yeah, perfect.
Then you can do 6 divided into 6 pieces. Let's see. Let me think about that. No,
Well,
no, that's not quite right.
No, because I need 12 on, so I can only put 3 segments, right?
No.
He's listening. Okay, so I posted you some documents to read to get you caught up, and if you read through those documents, you'll find a very short abstract of the theory, and then a few other modes of operations and thoughts by Dr. Roger Hastings, so go read those. Those are the 3 I attached. The one has a bunch of other stuff mixed in there, but go through it and find just the stuff that he wrote. And then in the book, section 2 or 3 or 4 has just one big pile of Dr. Roger Hastings data on the unit that looks like ours. I would recommend reading that as well. So there's 4 things you can look at that won't take you that much time. That should get you caught up to thinking about how we're doing what we're doing. Okay, Richard, what?
Six pieces, buddy. 110. The 110 degree needs to be cut into 6 pieces.
So let me ask you another question. Let's see if this is 0. Yeah, it's right at 110. So if I have 110 and I want 12 degree segments, right?
12 on and 6 off. If you do 12 on and 6 off, it'll divide equally into 6 pieces.
Yeah, but we want 12. Oh, so 12 degrees on, 6 degrees off.
Right.
Okay.
That gives you 18 degrees. 110 divided by 18 is 6.1, so it'll be almost exactly 6 pieces.
Okay. So I think what I can do is just make and break the positive side. I think I'm going to leave the ground connected and make and break only the positive.
Okay.
That way I only have to cut one and solder one, and then I don't have to go hacking this thing many more times than I actually really need to do that with.
All right.
So let's see, the inside is positive. No, the second one's positive. Because the ground, yeah.
So
we want to make and break on the positive.
Okay.
Hi. Because that's the way the current flows. From ground to a positive. So we want to make and break that one. I'm going to use the farthest outside one. See, that will be this one. So we're going to make and break. And I really need to, this isn't really centered, this is off-centered. How's that supposed to work? Maybe like that. Alright. So I'm going on for 12.
All right. Hey, somebody came to join you.
Yep. On for 12. 1, 2, 3, 4, 5, 6. Off for 6.
All right.
And then
On for 12.
12.
Actually, you could do on for 11 and off for 7 if you wanted to, but
No, the gap is good.
okay.
Off for 6. Twelve. 6.
You're going to end up with an extra big gap at the very end before it goes to the next one, but
These aren't precise, so I'll probably actually be about right. Okay. Let's see. That was. Let's see. Short, big, short, big. So I need a short. So 1, 2, 3, 4, 5, 6. 12. Yeah. 6. Got a short gap. 1, 2, 3, 4, 5, 6.
Just make sure you remove the 6s and not the 12s.
Yeah. Right now my goal is just to not hurt myself. It's not going to be perfect.
No, it doesn't have to be. I don't think it has to be perfect.
It's going to be like a... I'm going to leave the last one. There's a bit of an extra gap at the end. So I'm just going to leave it as a big segment instead of trying to peel it off.
Okay.
I don't see the reason.
So is it
It's a little longer.
18, or the last one is 18, or?
I'm not 100% sure yet.
Okay. It's all right. Good catch.
Thanks. I've done so much. Oh, you did it. To do what?
Go today. And just lay down a bit.
Okay, good night. There's one removed.
All right. 1 down, 5 to go, or 4 to go if you're going to leave the last one.
This isn't really... I guess it kind of is. Testing our other little theory. Should be pretty close to right. This will give us a good indicator of the on-off cycles during the induction cycle.
Well,
so I can rotate this because right now I have the big segments. Yeah, they're not. These aren't probably fast enough. I need to make these segments real fast if I wanted to do it the way I wanted to do it, but it's fine.
Well, I was just going by that document, you know. What
Yeah,
it said.
I know. We're just testing out that idea. This actually is not bad. Peeling this off like this, it's a lot smoother than I thought. I mean, I peeled the other ones off too, but I ground them off instead of cutting them.
Yeah.
I like polished them off.
Right.
And actually this is probably better because the surface of that fiberglass is like super smooth. But if there's any breaks, it doesn't matter. Anyway, I got one more to do, but it's soldered. So I have to unsolder it.
Wipe off some solder.
Undesolder.
Undesolder.
See, now I'm going to smooth these out. None for this part. Smooth, man. All right.
Okay.
I'll live. I ain't bleeding yet. I'll bleed in a minute.
Cut yourself?
Like always.
Oh,
Yeah, what do you want to do about it?
not do that.
Oh. Be wise choice. Luckily I used the dull side. Not the sharp one.
What do you want for dinner?
Nothing.
You're not hungry yet?
There we go.
You're not hungry yet, honey?
Not exactly.
Did you get the solder off okay?
Yeah, I got it off. Got it off. So that's the other question I had, is what happens if you make and break with one side of the battery connected, because now I've still got one side of the battery connected. That was another question I had, because that will result in, normally we're making breaking at the same time on both sides. Now we got a potential connected on one side, which will probably change things slightly.
Well,
I mean, this has been a question ongoing for a while.
yeah, I know you've been asking that question. I mean, according to traditional thinking, if one side is open, the circuit's open, and it doesn't matter. But
Yeah, not here.
yeah,
Here every little detail matters.
yeah, I know.
Because the coil is going to be on the ground side, though. It's going to be connected to the ground. So if current can flow back in one direction, it will still be connected to ground, but it won't have any other reference. So
Yeah,
I don't know what will happen.
I don't know either. I mean, if necessary, you can take the commutator back off and cut the other side.
Yeah, I can. I got to drill. Actually, I don't need to drill holes. I'm just going to wrap the wire around the outside. Hi, Lily. You guys should really be careful. There's a really ginormous magnet right behind you. You got a hair tie, it'll get sucked in there and you won't be able to get off.
No, but I have a piece of metal on my wrist. Yeah,
That's a cool idea. You should try that. See how that works. See how that feels.
what, this thing?
Yeah.
See if it works?
Yeah, on there. Do it on the top. Not sticking? It can't be metal. It's got to be made out of... Is it?
Yeah.
Oh, then it's got only a little. Lily, stay back.
I'm making it clean.
All right, well, stop doing that.
It's fun.
You might get sucked into a vortex.
I won't get that.
Where's the little bitty blue wire ahead? Here it is.
Man, your wife is stuck to the magnet. Mm.
Yeah, exactly. Yeah, well, I'll leave her there. She'll get off eventually. Richard said that you'd be stuck.
Yeah, I'd be happy when I have kids for a while. You can deal with it.
What was I doing? The inside, right? The inside. That one. So I'm going to solder. This is going to be tricky.
You have marks on your back.
Just use a tiny little piece of wire wrap wire.
I got some silver coated copper.
Yeah.
It's like 30 gauge, so I'm using it.
Yeah, okay, that's good.
1, 2, 3, 4, 5, 6. 1, 2, 3, 4,
I'm not going to pick it, but you have 4 dots on your back.
5.
Well,
But I only
6.
got 3 holes on the other side of this, so I got to be careful here.
For 6 segments, you only need 5 wires.
2, 3, 4, 5. No, I got 6. I got 5 breaks, 6 segments.
Right, so you only need 5 wires.
No, I got 6 segments, 5 breaks, with a 6th break behind it.
Ow! You okay?
Are you going to connect it across the 6th break?
You alright?
No, I got 1. I got a break, solid. I got a solder. 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 Break. Next section. So I have
Okay.
6 to solder.
Okay, I thought one was already connected. Sorry.
No. No, because that's how the... And this stuff is hard. Oh yeah, I cannot hold this wire at all.
Tweezers.
I'm not touching you, I'm rubbing your back. I am rubbing your back. Relax. Relax.
Are we gonna get chocolate?
Yeah, you want some food?
I want hot chocolate.
Yes, what else would you like besides milk chocolate?
You gotta eat some food too, Lily.
Need some fruit with it?
No, I can't.
You cannot. Want some mashed potatoes?
No,
What about some green beans?
no, not potatoes.
Want some potatoes?
Potatoes like daddy.
Like Daddy had for lunch?
Mm-hmm.
Okay, what else would you like? Anything else?
Potatoes.
Potatoes?
Potatoes like biting daddy.
Yeah. Did Daddy give you a bite?
Mm-hmm.
Is that for the...
What? I didn't give you a bite. There's still potatoes in there.
You saved that scope shot, right?
I did.
Yeah, okay.
With the cursors all over the different places.
Cool.
Okay. So this one's going to be... that one. Alright, that's those 3. Oh wait, 4. I'll put one
I
more
used
in
to
there.
work for a big defense contractor, and they have real strict regulations on soldering. In order to become a NASA certified solderer, you had to go to school for 6 weeks
Really? On just soldering?
just on soldering. Yeah.
6 weeks.
Yeah.
How do you know how to zip tie the military way? What is it, like
Well-
every inch or something?
I know
thought
a
it
lot of
was.
things. Unfortunately, I'm trying to forget most of them.
All right, good advice. Forget everything you learned once you turn. Well,
Mr.
That's
Google is
pretty
my friend.
I think the military zip tie, it's every 2 or 1 inch, I mean.
The one that was hard to do back in the old days was the military cable tie, where they had the string that you wrapped around the wires.
Yeah, exactly.
Boy, that was really hard to do.
Yep.
And that was definitely every inch.
Yeah.
You had to have a binding loop every inch.
That might be one of the ones I'm thinking of. I know somebody I know is talking about that. Plus, you can see it when you take stuff apart. It's pretty crazy.
Yeah.
It's a lot.
I mean,
but it needs to be that way if you really want it to stay together, right?
Yeah, I mean, it worked.
It's gonna be a bit tricky.
You wouldn't believe the tests I had to pass for soldering. It's just unbelievable. Unless you've gone through it.
Okay.
So I'm going to inspect your wheel and see if it's up to NASA standards.
Well, it probably won't be. Part of my problem
I'm joking, Russ.
Part of my problem right now is I gotta solder the tabs that I wasn't prepared to solder into. So I'm trying to keep them off the copper. I might have to adjust the brush so it doesn't hit these.
Yeah, just barely skim them onto the edge.
It's not easy. Solder just wants to go everywhere.
Yeah, copper likes to suck up solder. Solder wick works pretty well to flatten it out.
Good idea.
And then the brushes will just ride right over it.
Well, I'm not too worried about it riding over it. I'm worried about them hitting because they're pretty fat. I put carbon on it. Fatten them up.
Yeah, well, you should. I mean, solder wick should pull it down to level.
Yeah. This actually is not too bad right now.
Yeah, I noticed you're pretty skillful solderer.
Well, when frustration gets the best of you, you learn how to do it right before you throw everything against the wall. That's the way most of my skills have come. I'm either going to die trying to get it right, or I'm going to hurt somebody in the process.
And your perfectionist nature kind of urges you along.
Yeah, I am. My dad, he did good for me, and he also frustrated me at the same time.
Yeah. Oh, I know what you mean.
It's good though. It's all good in the long run.
But
hey, after soldering all those micro wires on those solar panels, I think my NASA soldering skills aren't too terribly bad, but they're probably not up to standard.
no,
those are NASA solar panels.
Like I said, I believe your soldering skills are pretty darn good. I'm just not sure you could qualify as a NASA solderer, but
probably not.
Very many people can, so
probably not. This ain't so bad. We'll be alright, actually. It's pretty good.
Cool.
As far as... The first one was a little rough, but these other ones... I'm soldering the wire and then trying to tack them to the pad. That's working a little better. First one got a little bit much. Okay.
All right. Woo.
I can handle that. Do I got them all? 1, 2, 3, 4, 5 to the center. And then, let's see, do I have them right? I hope I got the right ones. That one goes to that one. That one's shorted. And then this one goes to the outside. So do all those. 1, 2, 3, 4, 5, 6. I got 1, 2, 3, 4, 5, 6. The last one's a little long. The other ones are on par. If I cut the last one, then I have a super wide gap, so I'll just leave it a little long and we can see what the different charge time is on that thing. It's gonna go because I only did half this thing. So it's gonna power cycle through the other side.
It'll be interesting to see the difference between the two sides.
Yeah, exactly, because I did a short and a non-short and a short and a non-short just to see how that reacted, and it's a good way to see the difference because it's on the same shot. Should really use these other ones. These things are not very good for this. Yeah, this little PLA bushing, I threaded it. And then I cut all these, man, I cut these holes with the CNC. I measured the screw, right?
Yeah.
Then I cut them with the OSD. And I'll be darned if, man, it is exactly, I mean, it's amazing that that thing built from crap is just, it's just so, it's, I mean, it's in the micron range precision. It's just crazy.
Well, like I said, you're skillful.
All right, this bad boy is finished. Timing cycle, we'll figure that out in a minute, but that's about there. Okay, take this off. Put it back up here. Yeppa. Ba-ba. Man, this commutator design, woo, what a treat. This is easy to work with compared to that last setup. It's a bit rough. Then I can just switch these commutators out. Look at that. We made an adjustment in what? It's been less than an hour, right?
Yeah.
It's pretty cool.
Yeah.
That's gonna make sure the brush don't hit that.
Really, I mean, you could make a bunch of different configurations and get them all cutting while you were doing other things, you know.
Yeah, exactly. Yeah, I got that much smaller cutter. I could cut the segment. I cut the segments by hand last time just because I didn't want that huge gap in there. But if I get the right material to fill it in with, then that gap is fine.
Yeah.
All right, we'll see if they whack them.
So when you had 100 RPM yesterday, were you running at 300 volts or 600 volts?
This I calculated all this with the higher voltage.
Okay.
I think we like barely nick that one. I can bend it in a little more. Oh, that's so beautiful. Okay. The test shall begin, then the day shall be over. Because it's past my time. I gotta go take care of those children. 6 o'clock. Alright, I'll give this like just a little bit of time to crank up and then see what scope shots look like, and then I'll have to finish this later tonight or something. Did I put, I didn't, oh, I don't need to put this one back. Okay. All right, here we go. Run the scope. Bring the scale out a little bit. Turn the meters back on. What's the scope? We got the scope. We got the, is it updating? Oh yeah, it's updating. Okay, you ready?
Yep, ready.
Now we should see some serious, I'm not going to say it. That's a quote. Quote, man, 88 miles. And when this baby hits 88 miles, you're going to see some serious shenanigans.
Yeah, only if you got the proper number of gigawatts, buddy.
1.21 to be precise. The Libyans.
Yeah.
Okay. I don't know how they find me, but they did. The Libyans. Okay.
Knock, knock.
All right. So, boom, 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 boom. Oh, beautiful. All the way right through that power cycle, baby. So, just FYI, the segments are shorted at the end. So, we have a segmented short, and then a fire, 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 then a segment, oh, then another fire. Okay. Then a segmented short. Then the next fire. And then a gap, then a fire, then a short. So this should be the right polarity. What was that? Something scared me. All right, I'm gonna put this thing on the short so I can get it cranking. So I should be able to just connect this. I'm gonna zero out my probes. Green is on the coil. Purple is on the coil, current and voltage. Yellow is on the batteries, and blue is on the ground on the batteries. The green current probe is obviously switching polarity because it's on the coil side. So, that thing goes. I'll turn this cursor off, I'll zoom this back out, and let her eat, baby. Oh.
Oh.
So I hear it trying to speed up. I'm going to pause it. I'm going to disconnect it and have a quick look. Then I'll adjust the timing just a little. I think it's a little bit, needs to go back a little bit. So now, I don't think we have enough RPM to get a good induction going. Oh, a little bit. Oh wow, look at that first one. See, that's the short. That's on 5 volts per division, but look how high that voltage is right there.
Yeah.
Current's not too low, but that's, I think I need to adjust it, but that's because of the short. I know that's because of the short. The current's still going the wrong way, so as soon as you turn it on, it still goes the wrong way. I'll just save that one. That's 0004. Okay. Let's go over here and get that shot, and then we'll get a we also need to get I need this green blue one to come to the front actually. I can't see it. Should be about the same as the green, but actually no, it shouldn't be because it's disconnected right there. Okay, let's get a quick time. So time from here, oops, go from right there through both of the cycles over to here. That's about 680. We're pretty close to 100 RPM. Little slow.
Yeah, just a little bit.
I'm gonna adjust the timing just a little bit.
Alright.
It's connected. Let's see. I want it to be
About 88 RPM. Ooh, close to 88, buddy.
I need to actually. Oh, I see. I should actually switch a couple of these segments to make this better. So that's the fire. That's the short. And then it starts to fire. Boom, 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 boom. Okay. So I advanced it.
Advance the timing.
And we'll hook it up here. We'll run the scope. Faster.
Yeah.
It's smooth.
Yeah. Not drawing much current either.
Oh yeah, see that okay, so remember we're supposed to run at oh well, that was on minimum, by the way. We're supposed to run at about the self-resonant frequency. So the important part of this is that purple line. See that purple line?
Yeah.
That purple line is turning the coil back on or off at the right time. Now, if it were me, I would want to turn the coil on exactly when the purple gets to the top. That's a quarter wave input. Okay? This is just my thinking. If you turn it on at a quarter wave input, pulse it at the quarter wave input, then we turn it on when that peak is at its maximum. See, right now it's in the wrong direction.
Yeah.
And I would actually want it to be the opposite direction. I might spin it by hand and see if I can match that. I'd like to match that and see what a quarter wave input looks like, because that's how you can pump the thing, in my opinion. Just a totally another side effect of what I'm looking for. But I think I can.
Spin it, see what happens.
Yeah, I will. I'm going to save some shots here. You see the first one right there. There's a little bit of negative, a little bit of positive, a little bit of negative, a little bit of positive. Then I think it's actually outside of the induction window over here.
Yeah.
It's outside the induced voltage range.
You got the coil right up against the magnet.
I'm going to turn the purple down a little bit so we can see it. Oh, I already did. No.
Or are you back 3 inches?
I'm not back 3 inches. I'm back about an inch. So yeah, you can see the induction cycles near the end. And that's the short, then the induction cycle, then I'm trying to remember if it's shorted. Yeah, it's shorted after. Alright, I'm going to say this again. So that was 005, 6, 7, 8, I can't remember, 4, 5, I can't remember. They were above. Okay, let's get an RPM really quickly. Oh, I kind of turn those off sometimes. So we'll call it there, and we're gonna call it right here. Let's turn it on yellow so we can see what we're seeing. Pretty close, 509, so it's a little fast, but we only did half the commutator anyway. Now there's another calculation we need to do.
Okay.
Which is the quarter.
That's the res.
Yeah, what?
That's 117 RPM.
Oh yeah, but you see that? See the purple swinging in between each one of those?
Yeah.
That's more interesting to me. That needs to happen the whole time. If that happened the entire cycle all the way around, I think there would be some interesting things as far as resonance is concerned. But
okay.
because then you're turning the coil on and off when that voltage gets pumped higher, and then I think we'd see that step charging effect.
Yeah.
But then not the pulse, not the arc step charging, but this one. Because if you look at it, see right now it's, if I was hitting back. So if I could turn it off and I slam the thing and I get that voltage and current spike right there where the A is, if I could get it right there, then that energy would transfer into the next pulse. I'm going to try to do it by hand just to see if we can see any difference.
Okay.
I'm not so sure we're going to see the difference.
You're going to have to spread the screen out a little bit so you can see it from across the room.
Yeah, I did. Well, actually I went the wrong way. Just see where it's at for a second. Yeah, I can't see it, can I? See, if I bring this over, then I can see it. Not too far. Oh man, I still can't see it. It needs to be a little faster. But it's pretty good RPM.
Yeah.
Oh, yep. I hear it starting to flash. Oh, it's actually... What's it doing there? Skipping? Oh, no, the energy is flatlined. So, maybe not. I'm not sure what's happening there. Not quite enough. Actually, it's arcing over. See that? Right there on that would be like the quarter wave input. It's actually arcing over and it jumped into the circuit. See it?
Yeah. Well, what do I use? 500 volts per division?
Yeah, it's over.
Quite a few thousand volts there.
Yeah, because I could hear it. At a certain RPM, you could actually hear it. All right, I really gotta go. Now don't forget we're not shorting out any segments either. These are just
right. It's running pretty good.
Yeah, it's nice and smooth. I might adjust the timing a little bit more. See, right now it's shorting there, firing there. If I fire it way over here, it should run a lot faster. But the broken segments aren't really in the induction cycle. So the induction cycle, yeah, because I've got the firing segment. So it catches, the very last break is about parallel or 90 degrees with that coil. So the make and breaks happen before the induction cycle, basically. So I'm going to try that. This should run a lot faster now. Should be actually closer to what I was trying to spin it at. A little bit.
Ooh, look at that.
Look at that mess, man. I shouldn't have moved it until
The
I stopped it.
last one looked like it went quite a bit above the battery voltage. The last pulse in each series.
Well, the maximum on the scope, that little red indicator going up, is 576.
Yeah.
See how the induction cycle is at the end?
Yeah.
So it's not, so you can see the induced step charging effect there. That's not induced, I mean. Not induced step charging. Because it's past that point.
Does that mean you need to advance the timing more or retard it?
No, I need to retard it to get it into there, but I was trying to get it to run faster, and I knew it
Oh.
needed to be there. I could
Oh.
cut that one more next segment in those segments again and get it to go all the way through all of them. Basically what I'm doing is building our other commutator.
Right.
I mean, that's what I'm doing. Literally,
Yeah.
that's exactly what we're doing. We're building that other commutator.
Oh, I knew that.
It's just, I'm only doing a half cycle so we can kind of get a good comparison. Man, that thing's so slow with that. Alright, so I'm going to take a little speed measurement. 114, 115, call it 117. What is that? Still awake over there?
Am I still awake? Is that
Yeah,
what you said?
what's 417 milliseconds?
Sorry.
It's okay.
117?
417.
417. $143 RPM.
Okay. So we can go in here and look at this. Look at that. That's interesting. Oh, it is dipping negative. How about that? The current probe is going negative. Look at it. That's exactly the result. That's it right there.
Yeah.
How nice is that?
Yeah.
That's the arc between it. That's that high voltage arc going the wrong way, trying to collapse. Interesting. That is real interesting. I mean, the battery, it's not above, it's like not above ambient, it's like below ambient, but that's it though. Isn't that interesting? Look at that. That is just really interesting.
Look how the pink voltage peaks and then in the middle of that segment.
Yeah, I know. It's trying to arc. That's what I'm saying. It's going in the wrong. It's going in the. It's trying to collapse. The field's trying to collapse, and it's throwing an arc. Right. And then as it does that, now the thing is we don't have induction here at all. We're past the induction cycle. If we go. Oh, look at that. The last one didn't do it.
Well,
And the last one before that, after that, didn't do it. I mean, obviously we're let's see, is that, let me go back in. I need to look at that again. Let's go to a different one. Now the high voltage, it's going fast enough that the high voltage is arcing. But now we're not in the induced mode. See, we should be in the induced mode here, and that should be much greater effect. You know what I mean?
Yeah.
Because the battery voltage is actually dipping. It's going in the wrong direction.
Yeah.
Which is interesting. That's really interesting. Huh. It's interesting that now it's throwing that arc because it's going fast enough. So let me try this. I'm going to go try it by hand. So we can get it going fast enough to where when it breaks, it's doing exactly that. It's doing exactly that charging right there. But it's doing it in the induced field. That's where we should be for this test that I'm trying to do anyway. So I'm going to just completely put the timing. That sounds good. Right in the middle of those breaks. Boom, 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 boom. And then what I'm going to do is just spin it really fast. Let's see if we can get those. See if we can get that effect. But with the induced part. All right, let's just try that. Then I gotta call it quits. I can actually tell when it's doing it because it arcs over. All right, somewhere in there we might be able to see something. I don't know.
Like finding a needle in a haystack.
We got a lot of needles. Look at all of them. Let's go over here a little bit. I don't think it's doing that. Oh, we're only like half. Oh, there's one. There's one right there. The battery voltage. Oh, okay. That's part of the. It's part of the other cycle. See that negative? Yeah, right there. That big peak. That's current going. There's no voltage change there. See, I'm like nailing the cycle, so it's at 0, so it's not arcing. See it?
Yeah. Yeah.
I'm missing that window. I guess what I need to do is cut the other side similarly, but make it shorter. Cause see this last one's shorter than the other ones. We cut them 6 degrees. I should have stuck with like 4 degrees, so that the cycle would be shorter and then it would arc back over at that cycle.
Oh.
You know what I mean?
You could solder a little piece of foil in there.
I think if I solder anything, it might throw some stuff off, but I can try it. I mean, this commutator is going to be toast eventually because of the arc over it's had a few times. But look at that main one right there. I don't even know. Oh, there. Look, that whole cycle's above. What?
Yeah.
I'm confused. Let me go measure the... Oh, that's right, because I'm spinning it by hand. So even the low portion of that is well above the battery voltage. The battery voltage right now is at 574, and that's 578. So that entire cycle right there is negative.
It seems like it happens when it goes from the negative cycle to the positive cycle.
Yeah, it does, because see this right here where cursor B is a short. So current's still circulating in the wrong direction. And as soon as you turn it on, it's going the other way. You know what I mean?
Yeah.
But this won't happen by itself. I don't know if anybody watched the meter. Did the meter go negative up there on the left? It had to have. That's all negative right there, that whole entire cycle.
I forgot
That
to watch
whole thing is. I'll just see. I'll do it again without running the scope so I can just see what happens.
All right.
That whole thing should be negative. That whole cycle. Should be. Oh, I can't spin it that
I haven't
fast.
seen it flash negative.
I know, that's weird, because that whole entire cycle is above nominal voltage. Yeah, there it is.
Yeah, it did one time, yeah.
I think the refresh rate of your camera is slower than the refresh rate of that screen. Oh, no, maybe
Yeah, I
not.
know.
No, maybe not. This is only 6 times a second. But still
Yeah.
hitting and missing. Alright, I gotta call it quits for the day.
Okay.
But that's where we're at right now. Sorry I didn't read any of the chat, but yeah. I'll have to glance at it later. But anyway. Okay, Richard.
All right.
Thanks.
Thank you.
You're welcome. We'll continue this tomorrow.
Okay.
Alright, good night, everyone.
Good night.